ME204, Equation of Motion in Normal Binormal Coordinates. Let's look at an Olympic cyclist. Olympic cyclists race on a circular track, and as they go faster and faster around the track, they move further and further up the side of the track. The slope of the track helps keep their bicycle from sliding out from underneath them as they go around the curve. We want to know if we can determine the minimum speed a cyclist would have to travel to stay on the track without the wheel slipping out from underneath them if we know the slope of the track. How do we accomplish this? We'll start much the same way that we've started other problems, like normal tangential coordinates, and in Cartesian coordinate systems we need to draw a free body diagram and a kinetic diagram. So let's write out a full problem. We've got an 890 Newton cyclist, including the bicycle. They're traveling around a track at a constant speed. The track has a slope of 45 degrees and a radius of 125 meters. We want to know what the fastest the cyclist could ride without the bicycle slipping out from underneath them, and what's the slowest possible speed they can go. We're going to treat the bicycle and the cyclist as a single particle. The coefficient of static friction between the bicycle wheel and the track is 0.8. So let's start with our free body diagram. Here's our cyclist. We know that the cyclist and the bicycle have a weight, and that weight is 890 newtons. We'll also have a normal force pointing up perpendicular to the track. Then we're going to have friction, but what direction should the friction be? Should it be this way or this way? Well, it depends on if we're looking at the slowest or fastest condition. If we're looking at the slowest condition, then the friction would point up the slope, which would be opposite the direction that the bicycle wants to move. The fastest would point down the slope, preventing the bicycle from sliding up the track. Can we use that our friction would be equal to our coefficient of static friction times the normal force? We know that our static friction is somewhere between 0 and this amount, but can we use this exact amount in this problem? Yes, in this problem we can. We're looking for a point where the maximum static friction will occur. So we will use mu sub s times our normal force. Now let's look at the kinetic diagram. The cyclist is going around a circular track. The acceleration in the tangential direction is 0 because he's going at a constant speed. But because he's going in a circular path, there is a normal acceleration. That normal acceleration doesn't point down the track, it points towards the center of rotation in this direction. Now, when solving these problems, we need to look at a little bit different coordinate system. It's similar to our normal tangential system, but we have a normal binormal system. Our tangential direction is out of the page towards us, but the binormal direction is perpendicular to the normal direction. In this case, our bicyclist isn't accelerating in the binormal direction, or else he'd be coming up off of the track. Once we have our free body and kinetic diagrams drawn, we can go ahead and write our equations to solve the problem. Let's look at the fastest condition first. We start with looking at the normal direction. The sum of the forces in the normal direction is equal to the mass times the acceleration in the normal direction. We'll choose the direction of the normal acceleration as positive. In this case, we have a component of the friction, mu sub s times our normal force times the cosine of theta in the normal direction. And it's positive because it's going in the same direction as our normal acceleration. We also have a component of the normal force, our normal force times the sine of theta, and that will be equal to our mass times acceleration in the normal direction. However, we know that our mass is equal to weight divided by gravity, and our normal acceleration is the velocity squared divided by the radius of curvature. We can plug in what we know, and we end up with two unknowns, our normal force and our velocity, so we need another equation. So let's look at what's happening in the binormal direction. Our acceleration in the binormal direction is 0. So from our free body diagram, we have a negative weight minus the component of the friction in the binormal direction, which is downward, so it's negative, mu sub s times the normal force times the sine of theta. The component of the normal force in the binormal direction is positive, so we get a positive normal force times the cosine of theta is equal to 0. Substituting in what we know, we're left with one unknown, our normal force, so we can solve this equation for our normal force, which gives us 6,293 newtons. Substituting that value into our first equation and solving for our velocity, we get a velocity of 105 meters per second. If the cyclist goes any faster than 105 meters per second, the bicycle wheel will slip out from underneath them and they will crash. Now let's look at the slowest condition. In this case, our friction reverses direction. So our equations will be very similar, only the signs on our friction will be different. For our normal direction, sum of the forces in the normal equals the mass times the acceleration in the normal. Our friction, again, is negative because it's pointing the opposite direction of our normal acceleration. So we have a negative mu sub s, normal force cosine theta. Our normal force is still positive. Normal force times the sine of theta equals the mass times the normal acceleration. And then repeating what we did last time and substituting in what we know, we're left with two unknowns, the normal force and the velocity. Again, we look at the binormal direction and know that the sum of the forces in the binormal equals 0. Writing our equation, again, the equation is very similar to what we had at the fastest speed, only our friction sign changes direction. Now it's positive instead of negative. Substituting in what we know, we're left with the one unknown, our normal force, which can be solved to be 699.3 newtons. Substituting this value into our first equation and solving for the velocity, we get a velocity of 11.7 meters per second. If the cyclist goes any slower than 11.7 meters per second, the bicycle wheel will slip out from underneath them and they will crash. Our next topic is mass moments of inertia.